Hi everybody. This video deals with the pneumatic power system in the Turbine Pilot's Flight Manual, pages 68 to 72. Just an overview of this section. It's only 4 pages long. It also includes the APU, Auxiliary Power Unit, at the end of the chapter here. Now, what we need to know about the pneumatic system is it's air. And we know that air, unlike liquids, is a compressible gas. And these characteristics are a blessing and a curse. It's a blessing in the sense that when we use it for air conditioning, when we can compress it and expand it, we can cool it, we can heat it, we can do a whole bunch of things with it. But like a curse, it can't be used for heavy applications like hydraulics can. So anyway, here's another characteristic of pneumatic system. Unlike electrical and hydraulic systems, the pneumatic power system really does not have to have a circular pattern. In other words, with the electricity, remember, it had to go back through ground, back to the battery or the generator and go in a circular pattern for the electrons to flow. Same with the hydraulic system. Once the hydraulic system had powered the gizmo, the jack screw or the hydraulic cylinder, the excess fluid was routed back to the reservoir for reuse. Well, in pneumatics, we just let the bleed air, or not the bleed air, but we let the air go overboard because there's so much air available to us. We don't have to have that circular system. It's important to know. We just dump it overboard once we've used it. Next point is in turbine aircraft, we use the compressor section on the engines to supply the bleed air for use in the various systems, like de-ice, anti-ice, pressurization, air conditioning, etc. Another point is that in pneumatics, this compressed air is hot air. I mean, we're talking really hot. 600 to 800 degrees F, that's about 400 degrees Celsius. So we have to be very careful about the fire hazard and other things that are associated with these very high temperature gases that are going around the aircraft in proximity to fuel and other things that are very combustible. So they can be an ignition source for a potential fire on board. So we have to watch out for that and protect for it. We'll talk about that in just a minute. Okay, so let's go to page 68. At the bottom left-hand corner it says Pneumatic Power Systems. And the first T question is, the medium for power transmission is compressed air. Since air being a gas is compressible, pneumatic power is far less efficient than hydraulic power for heavy-duty jobs, as we saw with the hydraulic, the gear, the flaps, the control surfaces. Okay, let's go back to the top of the page here. Okay, it talks about the reason that the turbine engines are essentially giant pneumatic pumps. That's another reason we can dump this stuff overboard. The engines, we're taking them off, bleeding them off of the compressor section of the engine. Once we use the air to power whatever we need, we just dump it overboard. As you remember, reading from here, the engine's gas generator or the compressor section compresses huge amounts of air to support combustion. It's a relatively simple matter to draw this or bleed this air from the engines and to use it to power all sorts of things. Now it's interesting we use the word bleed because that's very applicable. We're taking some of the life force of the engine, the compressed air, and we're taking it off for other uses. So anytime you bleed something, you're taking away something. And we'll talk about this in just a little minute here, about when you use bleed air, you are robbing the engines of some power, and so you have to be careful, particularly on takeoff or go-around situations. So we'll notice that. Next T question, high pressure bleed air is drawn from the compressor section of the gas turbine engine. We've talked about that. Some systems draw bleed air from 2 or more stations on each engine, yielding different pressure and temperature outputs. These differing bleeds are sometimes identified as high pressure bleed air and low pressure bleed air. We'll talk about this. We'll have it's a very nice illustration he's got down on the next page. He talks about P2.5 air and P3 air. And we'll explain what that means. He's basically taking bleed air from different sections of the compressor, and they have different pressure and temperature. Now let's go down and talk about the high pressure bleed air. Remember, high pressure, high temperature. High temperature, high pressure type stuff, okay? So the high pressure bleed air has many applications straight out of the engine, including engine and wing thermal, anti-ice. Now we'll talk about, when we get to low pressure, de-ice. We haven't talked about de-icing, anti-icing systems yet, but this is a good point to just bring you up to date on it. As you notice, with the de-icing systems, like you see on most turboprop aircraft, you have a rubberized cover that goes over the leading edge of the wing. Underneath the rubber cover are some tubes that can be inflated with air, and as they inflate, they expand the leading edge of the wing, and any ice that's built up on there will be cracked and broken, and it will come off the wing. And so it's de-icing. You let the ice build up and then you take it off. Whereas anti-icing, which a lot of these high-performance large jet aircraft have, in fact almost exclusively, they have anti-icing where they channel hot, high-pressure bleed air down the leading edge of the wings where it keeps them hot. So any ice, those supercooled large droplets that hit the leading edge of the wing, are instantly vaporized and don't allow ice to build up and contaminate the airfoil at all. So this high pressure bleed air is used for that thermal anti-icing. Now we'll notice, as we talk back here, you can't turn on that thermal anti-icing on the ground prior to takeoff because it's so hot, 400 degrees C, that it'll damage the leading edge of the wing. So you have to turn it on once you get the air building up after takeoff. Okay, he talks about some of the other things that high pressure bleed air is used for. It is also used by a combination of air cycle machines. That's the ACM, air cycle machine. We'll get into that when we talk about environmental systems. A lot of times the industry guys call them packs. They're air conditioning packs, which take compressed air and cycle it through expansion and compression, and we can either heat it or cool it. And that's how we keep the air conditioning going inside the cabin of the aircraft. Now another thing that they can use the high pressure bleed air for is cabin pressurization. When you get to altitude, like the Gulfstream 650, I think, can maintain like a 3,000 foot cabin at 51,000 feet. That's awesome. It's got to use a tremendous amount of bleed air to keep that cabin pressurized to the point as if the passengers are sitting at 3,000 feet when actually the aircraft's flying at 51,000 feet. So we'll talk about cabin pressurization in following chapters, and you'll find that interesting. So bleed air can be used for this cabin pressurization, heating, and cooling. Next T question down. On large turbine aircraft, high pressure bleed air also powers the engine starters. He talks about the CFM 56. I think those are on the 767, the Boeing 767, are started pneumatically as an alternative to heavy electrical loads and motors required for electrical starting of turbine engines. So he talks about how they're started. They usually have what they call a ground-based compressor when they're at the gate, and this compressed air is put into the engine, starts the rotation of the turbine engine, getting up to ignition speed where it introduces the fuel, and the igniters starts the sequence going. On our smaller aircraft, we use a starter, electrical starter, but on these large aircraft, the loads would be just so high that they use pneumatic air to spin up the engines for starting. This is tedious, isn't it? Ticking through here. I found no other way of getting through the pages. Okay, page 69. We talked about the high pressure bleed air. Now we're going to talk about the low pressure bleed air and what's some of the things it powers in the aircraft. Okay, low pressure bleed air, page 69. Some high pressure bleed air is metered through a pressure regulator to much lower pressures, normally around 18 psi. So you can take the high pressure bleed air and through a pressure regulator allow some of that at lower psi to come through for some of the duties that it has to do, as it says down here. Low pressure and turbine aircraft drives air gyros, pneumatic de-icing systems. We talked about that. Low pressure may also be used for mechanical control functions such as valve actuation. Remember, electronically, valve actuation was used through a solenoid or a relay, but you can use air pressure to activate certain valves, or other things that can use low pressure for control of pressurization outflow valves and inflation of door seals to sustain pressurization. Now, we haven't talked again about pressurization, but at the back of the aircraft, usually when you pressurize an airplane, the inflow of air, of compressed air to pressurize the aircraft is from the front of the aircraft, and at the back end of the aircraft they have what they call outflow valves. So the pressurization control a lot of times uses low pressure bleed air to regulate the pressurization system in the aircraft. And the outflow valve is at the tail end of the airplane where it can, if the pressure gets too high, it can allow some of this compressed air to go overboard so the fuselage doesn't get stretched too much during the pressurization function. The inflation of door seals, you may laugh at that, but no, that actually happens on the King Air. We had inflatable door seals. Doors are where you lose most of your pressurization in flight. So they have to have seals around those openings. And a good way of marginalizing that loss of pressurization air is to have an inflatable door seal. So that's some of the stuff that, again, low pressure air can do. Let's talk about some of the hazards of using pneumatic, hot, high-pressure bleed air. And we've talked about them before in our overview of this chapter, where we talked about the high temperature of compressed air. I guess I'm getting ahead of myself here. Let's talk about, in fact, we talked about bleed air, bleeding power from the engines when you select that. And up here he just talks about that, and he says, therefore, in most turbine aircraft, high-pressure bleed air use is restricted during takeoffs and go-rounds. Again, you are taking away some of the power of the engine, and so you want to, after you get airborne and get things straightened away, you can select the bleed air for the various purposes. But during takeoff, you want maximum power available to you, or on the go-around. And so, again, bleed air can bleed it of some of the power. He goes on to say that sometimes weather conditions at takeoff do require the use of high-draw bleed items, such as engine inlet anti-ice systems. For those situations, most turbine aircraft have correction factors in their takeoff power and performance charts, often restricting takeoff weights and or speeds. It goes down to talk about the use of bleed air for thermal anti-icing is virtually never permitted for takeoff. Not only do the bleed sap lots of engine power, but on the ground, the 600 to 800 degrees F bleed temperature can weaken the aluminum wing edges, leading edges. So that's an important consideration. Now, he sometimes jumps back and forth between Fahrenheit and centigrade. As you'll see on the illustration down below, he talks about P3 air, P2.5 air, and he talks about as 175 degrees Celsius and 390 degrees Celsius here. Well, if you do your calculation, what's 390 degrees Celsius is roughly 760 degrees Fahrenheit. So he jumps back and forth up here, 600 degrees to 800 degrees. But down here, when you get P3 air, or the air coming off that high pressure turbine, the turbine, I'm not high pressure turbine, high pressure compressor, just before it goes into the combustion can, it's really hot. And so you can see that difference between Celsius and Fahrenheit. Good illustration here. The P pressure stations are defined by the engine's manufacturer and increase in order from front to back of the engine. Okay, so on the test I'll probably ask you, where is P 2.5 air taken off of the compressor? And you'd say it's probably at the low end of the compressor. Then the P3 air would be from the high pressure compressor. So if we had a P 2.0 air, it would be even more farther up front than the P 2.5. So it's important. You say, gee, this is Mickey Mouse. We don't have to be mechanics. Yeah, when you get into the ground school, they'll talk about P3 air, P 2.5, and so you need to know that the 2.5 is from the lower compression section of the engine. Down at the bottom of that page, bleed air is drawn from one or more of the points in a turbine engine's compressor section. Pressure and temperature vary based on location from which the air is drawn. Fairly straightforward, okay? Again, we were talking about the potential for fires from hot bleed air getting around fuel or other combustible materials. And this is really a key thing. Fire in flight is deadly, and so you have to watch out for it. So a lot of times temperature probes are often used to monitor the passages carrying bleed air lines. So they got temperature probes in there that'll pick up any temperature fluctuations as things get too hot. On the King Air we had a EVA system, ethyl vinyl acetate. Now this tubing ran right beside the bleed air lines. So if there became a leak in the bleed air line, it would heat up the EVA tubing, and the EVA had low pressure air going through it. So if the EVA tubing melted, some of that low pressure air would escape, and it would say, oh, we've got a bleed air leak in the system somewhere, and we'd have to shut down that pneumatic system because we would worry about a fire or something like that. So this EVA tubing, it's not over top of the pneumatic line, it usually runs beside it, but if there's a leak in the primary bleed air line, it will melt the EVA tubing, and that will give you your indication that you got a problem. Some of the compressor things, it says redundancy over here at T question. Redundancy is accomplished through the use of bleed sources from all engines and sometimes from the APU, the auxiliary power unit. We'll talk about that in just a minute. System like what are the check valves in the electrical system? Should be on your flashcards. They're the diodes, right? Diodes only allow electricity to flow in a certain direction. In the hydraulic system, they have check valves in there. In the fuel system, they have check valves in there. So our check valves in the pneumatic system are important also to make sure things go in the right direction. Isolation valves. This is the only area in which we kind of hear this term, an isolation valve. Allows separation of interconnected bleed systems in the event of a leak or other failure. So we'll see down in the diagram down here, he'll have an isolation valve. Anyway, let's look at this diagram for the time being here. We have high pressure bleed air coming off. We have low pressure bleed air coming off of here. And then we have coming down through here, we have that pressure regulator which takes it from high pressure to low pressure. And then it's used through here for pressurization, de-icing boots, instruments, gyro instruments, inflatable door seals, pressurization outflow valves. So again, this light colored stuff is low pressure, and the hot, high pressure air is coming through here. So this might be, usually an isolation valve, this wouldn't be called an isolation valve, but it's very similar to what it does. It just shuts off bleed air to a certain system. So we have high pressure bleed air coming through here, check valve, going through here. Again, here is the bleed air from the other engine. And we could have an isolation valve right in here so that if there was a problem with the bleed air from this other engine, we could shut it off from coming through into here. Or we could stop air from here going into the other bleed air system on the other, coming from the other engine. This just shows how you could use, if you had an APU on here, you could use that for engine start. So you'd wind this thing up. Once you get one engine started, you can use the compression from that to start the other engines. In fact, I think that's what happens on those big 4-engine aircraft. They start one engine, possibly using a ground-based compressor, or the APU at the back of the airplane. They start one engine, then they use a valve to open, going from one engine to the other to give it bleed air to start up the other 3 engines. So again, we have the hot, high pressure air going to the thermal wing anti-icing. And then coming back through here, we have the first stage of heat exchanger. This would be for your environmental packs or your air cycle machine, ACMs. And we'll talk about that in subsequent chapters, where they compress it and then they expand it and cool it. Then they compress it again and expand and cool it. So you can get the temperatures quite low by going through a couple of cycles like that, and that's why they call it an air cycle machine or a air conditioning pack. Let's go to page 71. We'll talk a little bit about our auxiliary power unit. I have never flown an aircraft with an APU on it. That is considered to be a real luxury on board an airplane because it has so many good uses. But I've never flown an aircraft large enough to have an APU on board. So anyway, APU, auxiliary power unit, is a small turbine engine installed to provide supplementary aircraft power. APUs are often found in the tails of aircraft ranging from large turboprops to jets. Interesting, during World War II, the B-29, remember the super fortress that dropped the atomic weapons on Japan? They had an APU in the back of their aircraft. It was simply a small gas-powered piston engine, and it would power a generator that would give them backup electrical power if something happened to one of the generators on the 4 engines. Okay, so let's talk a little bit about the APU. So it's in the tail of the aircraft. APUs are installed on dedicated generators to provide auxiliary electrical power in addition to that provided by aircraft engine-driven generators. This is valuable for running aircraft systems on the ground. That's where we like it. Without having to power up the engine, especially at facilities where no ground electrical power is available. I remember going to Nantucket and Martha's Vineyard in the summertime, taking the rich and famous out there, and we'd have all these executive jets on the tarmac, on the ramp, with all their APUs running. In fact, the people around the airport got so ticked off that they made the airport restrict the use of APUs so that these guys couldn't run them all night. Sometimes the crews would be waiting for party people to come back at 2 or 3 in the morning, so they just keep the APUs running all night. Well, it didn't bother the homes surrounding the airport there, so they had a limitation on the amount of time that people could run their APUs on the ground at some of these smaller airports like that. But for the crews, it was great. For the people around there, it was kind of noisy. Okay, so applications include powering environmental systems such as air conditioning on the ground, supporting maintenance of major electrical systems, and providing power for crew functions such as pre-flight. In other words, you got to get the clearance, you got to talk with dispatch or something of that nature. You can power up your electrical systems without draining your battery or having to start an engine. You can use, say at night you need the cabin lights on for cleanup and galley operations. Again, you got the APU sitting there. One of the important functions of the APU is it can be operated in flight, providing backup power for the engine generators. For those of you who remember Sully Sullenberger, remember the guy who had the double engine failure on the Airbus 320 there out of LaGuardia when he put it in the Hudson River? What was the first thing he asked the co-pilot to do once they found they had lost power on both engines? He said, get the APU going. So he wanted to make sure he could communicate with the tower, with the departure, and so that's a normal thing, is get the APU going. If you lose complete power, you've got that source. And we'll talk about, well, we talked about the RATs, ram air turbines, give you some power also, but the APU is the quickest way to get power onto the aircraft, and quite a bit of power. APUs on many aircraft can be used to provide backup pneumatic power for pressurization in flight. Anyway, APUs on many aircraft can be used to provide backup pneumatic power for pressurization in flight and to back up environmental systems on the ground and in the air. So again, some APUs just have electrical capability, but others you can bleed air off their compressors and use it for the aircraft systems also. So again, you have to watch which systems you can help, but every APU I know has got an electrical generator on it. Some of them don't have the bleed air. So let's look down here. Again, we've got auxiliary bleed power, we've got auxiliary electrical power, and you got your APU door on the side, and then usually you got the exhaust coming out the tail there. Let's go to the next page. It's got a nice diagram of the APU. We'll just leave it at that after we talk about this is the APU. As you can see here, you have the air intake